Let's start discussing equilibrium again by looking at a little example to remind you what we were discussing before spring break, Le Chatelier's principle. If you recall, what we discovered in our activity with the pennies is that equilibria are active, that is, a chemical reaction can still be occurring even though we're not visibly observing any change, because the rate of forward and backward reactions will have become even. And what we observed because of that active equilibrium is that a system in equilibrium can respond to changes. So when we took away some of the reactant pennies, our example system reattained equilibrium by shifting backwards from products to reactants. Now, pennies are a nice example, but this is a chemistry class, so let's look at a chemistry example. We're going to be looking at the equilibrium between a water complex of copper 2 and its equilibrium with a chloro complex. Now, this is a particularly good case to use as an example because we can take a fairly straightforward approach to looking at it. Now, one of the interesting properties of cobalt is that its color changes based on the number of ligands coordinated to it. This cobalt complex has 6 ligands, so we would observe it to be light pink. By comparison, this chloro complex contains 4 ligands in a tetrahedral geometry, and we would thus expect to observe it as blue. Now, what this means is that we have an equilibrium between 2 different compounds that depends on the amount of various species that are present. So if we were to, for instance, add more chloride ions, perhaps by adding something like sodium chloride to the solution, what do you think would happen? Pause the video and think for a minute about which way you think the equilibrium would go. Okay, so if we're adding more chloride, that's a perturbation, an increase in the amount of the chloride floating around on the reactant side. So that would mean that we would shift towards the product side. The result would be that if our system was at equilibrium, looking something kind of purple in color, we would observe it becoming more blue as it shifts its equilibrium. So compounds present with some particular concentration can be an example of being added or removed. We could, for instance, remove some of this chloride as well. What do you think you might add to this solution to make the chloride go away? So if it were me, I would add in some silver ions, perhaps a solution of silver nitrate. If you recall, silver halides are one of our solubility trend exceptions, and that means that when you add in that silver, you're going to be precipitating some of these chloride ions away. If you were to do that, that would shift the equilibrium back towards the reactants to compensate. The result would be that the solution would go from blue to pink. Now, adding or removing chemical components is certainly a part of how this can work, but it's not the only story when it comes to equilibrium. If you recall, back in chapter 6, we learned the idea that there can be various classes of chemical reactions and that different compounds can result. But then in chapter 7, we said that the types of compounds weren't the only things that we cared about in a chemical reaction. Energy could also be acting as a reactant or a product in a chemical reaction. So if this reaction were instead one where we had some heat necessary to make the reaction happen, in that case, we would be dealing with a reaction that is what? Endo or exothermic? Yeah, this is an endothermic reaction. So, in this case, to normally drive the reaction forwards, you might, for instance, add some heat. But if heat is behaving as a reactant, then cooling the reaction down is, in effect, removing heat from the system. It's like removing a reactant. So this is a case where if the solution was blue, you could cool the solution down and you would expect it to turn pink. This kind of reasoning about what would happen when you add or remove energy or new chemical compounds from a chemical reaction is a type of reasoning that's pretty valuable to be able to do. You can definitely expect on this week's quiz at least one problem that describes a reaction like this one, and then asks you to talk about what might happen when you make some particular change to the system. Now, this is very nice to be able to think about and to be able to do, but we're still ultimately talking about a process that is qualitative here. In effect, you may have even seen this type of problem in Chem 103 last semester. So up next, we're going to look at how to get quantitative about equilibrium.